Great. Yeah, I'm just imagining all the COVID diagrams with the molecules and things like that. Do you remember from like COVID when they showed the animations of the particles spewing into the air when people spoke like singers?
Okay, welcome everyone to our Minikanren and relational programming workshop. Glad to see you all. We have some quite amazing talks today. Please, those who are watching our stream, don't hesitate to ask your questions in our Discord server or the comments under the stream. And without further ado, please welcome Chris to the stage to talk about high-performance logic programming.
Yeah. Oh, okay, this one's working. So try that.
Great. So I'm going to be talking a bunch about Datalog in this talk. So if you know miniKanren, you can surely figure out Datalog. It's not a very complicated language. So I'll be using this example of transitive closure a bunch throughout the talk. So we've got two rules here. The first rule says that whenever we have a fact edge of xy, then we have to learn a new fact path of xy. Right, and the second rule, which is kind of a recursive rule, and this is the thing that gives us kind of the power of Datalog beyond SQL, because it can iterate, is a rule that gives us transitive paths. So this rule says if we've got a path from x to y, and this is something that could be arbitrarily going over the course of the execution, and we've got an edge from y to z, so we can extend that path by sort of one length, then we have a path from x to z. All right, so Datalog is a very trivial language. There's nothing really cool or fancy about it, but it's just pure chain-forward saturated reasoning. So compared to a language like miniKanren or other logic programming languages where you can really search, it's not a very sort of interesting language. And why is that? We're going to see, but it's because once you learn a fact in Datalog, Datalog's evaluation is typically tabled. You can never unlearn a fact. All right? And what this means is that any intermediate fact that's not part of the desired sort of solution set represents additional space complexity that you have to carry around, and if it's not something that you actually need at the end of the day, it represents some extra overhead that you don't care about. So for example, it's totally possible to write k-click in Datalog, and of course this should throw up red flags for us, because of course we know k-click's not an easy problem. But to get k-click, you have to materialize, you have to table all of the clicks of less than size k2. So that tells us that it's NP complete. So it's a dirt simple language with an extremely simple semantics, saturated chain forward reasoning over horn clauses. From a logical and semantic perspective, it's not that interesting, but its simplicity gives us kind of a good price point for scaling some useful applications. And these are applications where the problem structure is an exact match for Datalog semantics. So you can think of them as morally extensions of transitive closure. So reachability-based control flow analysis is a good example. The largest and most scalable control flow analyses of, for example, Java, including dupe, which is a system that's been scaled up to very high amounts of context sensitivity, even using things like adaptive context sensitive techniques. Those are implemented using state-of-the-art Datalog solvers. Other things include superset disassembly. So this is the challenge of basically you have a stripped binary, you don't know where the entry points in the binary are. And if you're on x86, for example, if you start at any sort of byte, you might find a valid instruction, of course, because x86 is very dense. And so there's this recent idea of superset disassembly, which basically says, try to start disassembling from every offset. And then you can start to see things like, okay, well, if I pick this disassembly, I get an unaligned pointer access. So that's probably not what it is. Or you could consider all of them and then use something like heuristic to decide which is the best fit. So there's a tool built by Grematech called Datasasm that also runs on Souffle and is kind of the best disassembler in terms of working with stripped binaries. I think this previous state-of-the-art on sort of reassemblable disassembly, meaning you can get back what you started with, which I would argue is really a prerequisite for doing any kind of binary instrumentation or hardening. The previous state-of-the-art in that over a large corpus of binaries was Rambler, and that was about 70% rate of being able to reassemble the thing that you started with. And Datasasm is, I think, past 99% on a fairly large corpus of, let's say, Linux ELF binaries. And you can also use it for traditional knowledge representation and reasoning tasks like semantic web. So there are other solvers, proprietary solvers like RDFox that are kind of built for tackling these sorts of tasks as well. Some of these have slightly separate domains. For example, they might focus more on incrementalization and stream processing than our setting. We're kind of more restricted, at least at the current point, to mostly kind of batch processing. But true incrementalization is, we use incrementalization under the hood to implement our solvers, but we don't have things hooked up to like a streaming interface, for example, yet. That's something we're interested in looking at as well. So saturated, iterated, reachability-based reasoning is kind of Datalog's bread and butter, and that's a lot of what I'll be talking about in this talk. So we've got three, at least what I think of, are state-of-the-art systems. If anyone thinks they can beat them, feel free to let me know. We're very interested in adding them to our evaluation sets. So we have a SIMT, which is a modern Datalog system that's embedded in Rust. It beats, in terms of speed, the state-of-the-art system Soufflé. It gets quite good parallelization up to around 32 cores of, say a 64-core EPYC AMD server. Where, for example, Soufflé, we see the scalability kind of fall off a cliff around 4 to 8 threads or cores. And, but we are not quite as memory efficient, and so I'll talk a little bit about that later. Another system that I'm going to talk about, at least I'll talk first mostly about Ascent. I'll talk a little bit more about Slog, which is our distributed system. We've been able to scale up Slog roughly to around 16 to 32,000 threads, and that's on the Theta supercomputer. This is a supercomputer that is got a very high performance interconnect. The one I'm showing here is Polaris, which is the computer that's replaced it, which we're also running Slog on. The constant factors in this system are quite high because we're using MPI. So compared to a SIMT, you'll have to see that you'll need to take several hundred threads to recoup your sort of communication overhead that you would get from maybe a really well-written SIMT program. And there are lots of restrictions in Slog due to the fact that it's truly distributed. So having unified sort of memory allows you to write some things much easier. For example, union find data structure. It's not obvious how to implement that in a distributed setting, at least in Slog yet, something we're kind of interested in working towards. And then one thing that I'll talk about quite briefly at the end, because this is really kind of ongoing work, is our recent work on scaling Datalog on modern data center GPUs. And we found quite promising results. So we've been able to beat Soufflé by a factor of, it says 100x here, but one of our more recent work is up to 200 times. On an NVIDIA H100 versus an AMD EPYC. So it's not an apples to apples comparison because the memory bandwidth isn't quite the same, but we've had good performance, and I'll talk a little bit about how we've done that. So I will start by talking about traditional Datalog implementation as you might do it on a unified machine using kind of a modern solver. So our system, Ascent, is a state-of-the-art Datalog engine that's embedded in Rust. It was written by my PhD student, Arash Sahib-Alamri, during his PhD. The key novelty in Ascent that I think people really like about it, it's a crate that folks in Rust actually use. We've used it to great effect. And I think the thing that's really exciting about Ascent is the fact that you can integrate completely with all of Rust's traditional data structures. And especially if you want to do something like write a large analysis of LLVM, which we've done in collaboration with some folks at Galois, we used Ascent to write 2,500 Ascent lines of a control flow analysis for LLVM that's like a context-sensitive analysis. And we were able to use all of the standard LLVM crates in Rust to do this, where if you wanted to do this in Soufflé, you would have to figure out how to linearize all the data structures and put them into CSV files, call out to Soufflé. You would have to compile the Soufflé code separately. You would have to maintain it separately as Soufflé evolves over time. And so I think that's the real exciting part of Ascent. In terms of the compilation, it's nothing extremely innovative versus the state-of-the-art. There is a unique approach, though, which is that we use procedural macros. And then we do have an innovation versus Soufflé that I think is kind of a slightly more exciting one, which is the bring your own data structures approach. And this approach, which we published at Uppsala 23, allows you to get past the problem of the fact that in traditional Datalog engines, you have kind of a fixed choice of tuple representations. And if you, for example, say, I want something like a union finds data structure to be able to represent relations, because I know for a specific task that I might need that ability to do space compression. Well, if you were to do that in Soufflé, you would either have to use one of the built-in relation providers, or you would have to go learn all of Soufflé's API, write a bunch of gnarly C++ code, recompile it, all of that yourself, which we found very hard to do. You can sort of do it if you're, a real serious research engineer who spent serious time looking into Soufflé's API, but Biodes offers a very pluggable interface to be able to accomplish that. So just to show you a little bit of SIMT code, so I've got some SIMT Rust code here on the right. So first we load all of the SIMT macros. So SIMT is a macro-based system. We use procedural macros. This little SIMT bang block invokes the SIMT compiler, which parses the SIMT code, turns it into various stages of IRs. I'll talk about the compilation methodology for Datalog. We use all of the standard kind of modern compilation methodology, primarily influenced by Soufflé. So we've got some code here that recapitulates the transitive closure problem. So we've got this first rule, the second rule here from a few slides ago. And then this line down here at the beginning of main scaffolds an SIMT program. And that comes from the SIMT bang macro. We then populate a bunch of edges. And then we run the program to a fixed point. And then we can print out prog.path. And so SIMT macros set up the various relations declared in the relation block so that we can use them later after the fixed point is executed. Okay, so we use most of the tricks from Soufflé, which is kind of our main inspiration for how to compile high-performance Datalog code. There's been a bunch of different strategies for compiling Datalog that primarily have dealt with various trade-offs that we've faced over the years. So I guess I have a few slides about these. I'll talk about them in a second. But I guess I would say our key novelty really in SIMT is trying to improve upon the ergonomic concerns. We're not trying to do much innovation directly in the compilation. We're trying to take a macro-based approach rather than writing sort of our own compiler. We're trying to integrate with Rust and get as far as we can by doing that. But really our sort of technique and our kind of real innovation here is to be able to allow a Rust programmer to be able to integrate with the kinds of data structures that they might use on a day-to-day basis, rather than having to use something like a U64 or a string or a set of sort of just primitive types that you might be able to get in Soufflé. So I'm going to give a little bit of a crash course on compiling modern Datalog, at least as inspired by Soufflé. There are various other ways to do it that I'll talk about, but Soufflé currently gets the best-in-class performance. So there are a few different concerns that I outlined here. So one of the first ones is data structures. So it's very key to have efficient data structures, especially because most modern Datalogs are parallelizing. So for a while, folks tried things like BDDs. That was one popular instance of Datalog compilation. And that was very useful when we didn't have very much RAM, because we could enumerate much larger Datalog programs. But over the course of the years, machines got more RAM, and we started to really care more about kind of raw throughput. And so modern implementations often use explicitly materialized representations of tuples, although we'll talk about how you might deviate from that in Biodes in a little bit. And so Soufflé has some especially well-written, fast concurrent data structures that are minimally locking. And that's a lot of how they're able to get their good speed on the face of performance. You also want indexing. So you want to track multiple copies of a relation depending on how it's used, so you can do efficient range querying. So I'll talk a little bit about that too. You absolutely need semi-naive evaluation, which is a strategy for incrementalization, basically not rediscovering stuff that you've already learned on every iteration. And the fact that Datalog has a very simple monotonic semantics really guides that. If you try to start doing more proper search, then that really challenges semi-naive evaluation, and that's one of the kind of key concerns in the algorithmic side of extending the language with respect to its expressivity that I'll chat a little bit about. Most engines do compilation to relational algebra kernels. All right, so I'll talk a little bit about that. And then one thing I won't talk too much about is different join strategies. So there have been various engines over the years that use various join strategies. I'll talk mostly about nested loop joins over explicit representations, but there have certainly been other solvers. So if people are familiar with logic blocks, they use leapfrog trijoin, which is also a very beautiful algorithm, but just hasn't proved scalable for parallelization and things like that. And there are also some novel algorithms like free join and things like that that we're looking into adapting to our engines as well that are also interesting and we can chat about offline if you'd like. So as I said, Datalog's seen many resurgences over the years, and I think these mostly coincide with different constraints that people face at different times. So of course, there was some famous work by Whaley and Lamb at PLDI 2004 using BDDs for global points-to analysis. And then that work has been kind of iterated upon and brought to maturity in the form of a system named dupe for Java, which really scaled sophisticated points-to analysis with a wide variety of context sensitivity, a rich notion of being able to choose various kinds of sensitivities with different trade-offs. And that system, dupe, has been very enduring and still represents kind of the state-of-the-art in context-sensitive analysis of Java today. And so these days, Datalog focuses more on parallel evaluation over explicit representations rather than, for example, BDDs. But we can talk a little bit about the different trade-offs there. So dupe has a few different representations that it uses under the hood. They're all concurrent. There were two papers that came out around the same time that describe the main ones. So the one that's used most often is basically a parallel and concurrent B tree. And then another one is trie called Brie. Now this one doesn't seem to perform as well in many applications. The reason is just that the trie structure ends up inducing more locking. So there's more lock contention and write contention when you write out to relations. And that's something we'll see a little bit in our experiments later as well. All right. So we also use indexing. So if we're going to use nested loop joins, here's basically how they work. So a join like this between path and edge, we have a few different options. But one option is that we might iterate over path and then range index or range query edge on the first attribute. So we iterate pairs of x, y, and then we need to efficiently select the set of z's for each y. And so we could make another choice. We could also say that we might iterate over edge, and then we might kind of look up. And it depends kind of how the rules are written, kind of what you choose to do. And depending on the relative sizes and dynamic performance of the program, one of these might be better or worse than the other. There are some good low kind of worst case bounds out there that dictate what the size of intermediate products and breaking apart sort of k-array joins might be. So if you're interested in those, feel free to chat. And one thing that we haven't really done much, but seems like it might be exciting, and some engines have attempted to do this, is trying to do join planning dynamically. So kind of across the course of the program, trying to see how to change kind of a join plan over time. So if you organize relations as tries, you can save a little bit of space. So you might be able to recognize that you can reuse an index. For example, if you use something like, I think I have an example of it on the next slide. Oh, no, I don't. Let's see. I put these slides together pretty last minute. But if you have something where you might want, for example, x, y, and then also x, well, because it's organized as a trie, you have to go through x to get to xy. And so if you just store xy, that's kind of all you need. And so this is a trick that's used in Soufflé. In fact, Oracle currently holds a patent on it. And it is used to sort of lessen the space burden. But it comes at the cost of more write contention. So we've also implemented this trick in Bjodes, which I'll talk about in a little bit. But in their implementation, so this is a VLDB 2018 paper, they were able to get sort of 2x space reduction on average, and that's over a large Datalog program. It's over essentially a large, I think all of dupe, so thousands of rules. So it's not a massive win, but it does allow you to, at least with respect to some linear factor, reduce the space overhead if you can organize relations this way. So in semi-naive evaluation, we process only new facts. So what we recognize here is that without kind of incrementalization, at every iteration we have to rediscover every previously discovered fact. And if you've ever written something like a frontier semantics for something like a program analysis or a state space exploration that has kind of a monotonic flavor, you'll be familiar with this idea. Or essentially, even if you, and this is one that I actually do have a diagram of, so to show, if we start with our kind of first iteration here and we're trying to do transitive closure, in our second iteration, we don't want to have to rediscover all of the grayed out stuff. We only want to discover the paths kind of that are of length 2, and then over the course of time, length 3, length 4, length 5. So semi-naive evaluation is justified because of monotonicity. We never kind of unlearn any data. And indeed, extending semi-naive evaluation to the case where we have sort of non-monotonic or apparently non-monotonic programs, it's an interesting, a challenging, and kind of an important area of open research. But sometimes being able to delete facts is necessary. So there are various ways that we can do that. I'll talk about things like union find. Other approaches include e-graphs and things like that. But in general, if you start deleting facts, then semi-naive evaluation kind of breaks. And so there are various ways you might try to reconcile that, like you might try to, for example, try to track dependence or provenance of facts to decide how you can do that optimally. There are some algorithms that try to look at that. But this is essentially why Datalog can't search. You can never really forget information. And if you try to use Datalog to search, you're destined to remember all of the sort of intermediate state that you enumerated. So this is kind of an interesting and open problem. Within databases, this problem is kind of related to something called recursive aggregation or lattice aggregation if you're studying programming languages. Okay, so SIMT implements most of Soufflé's ideas via procedural macros in Rust. We focus on easy integration with traditional Rust data types and libraries. In practice, we found that this was really the biggest win. So in terms of the actual ergonomic, being able to reuse standard Rust machinery for common tasks like doing analysis of LLVM or other things like that, that was hugely useful to us. You didn't have to, I think one thing that's kind of underappreciated is the fact that if you look at traditional implementations of things like program analyses and Datalog, you have to take complex linked data structures and linearize them as sort of flattened tables. That's something we've a little bit worked on with another aspect of my talk that I'll talk about as long as I can, our language slog for structured Datalog. But this was one really nice thing to come out of SIMT. And you don't have to understand this, but just to show you kind of a high-level idea of how it works, if we take the program on the left, or sorry, the top right, and then we run it through the SIMT macro expander, we get this larger program down here, which implements all of the standard machinery that you might see, for example, in Soufflé. So our initial version of SIMT was published at Compiler Construction 2022. We didn't have index selection or parallelism, so we weren't properly completing with Soufflé at the highest level. We got acceptable, within a factor of 2 or 3 performance on a single thread, but really scaling up is not something we were able to do with this initial implementation. So that was really focused on just the ergonomic integration. And also another thing was that SIMT, even in that version, had proper lattices. So that allows you to step past the traditional power set lattice, which is important if you're trying to do some kinds of program analyses or other sorts of tasks. And lattices allow you to get a little bit of this flavor of being able to do search because you can, if you have lattices that are not the power set lattice, you can kind of delete information in a sort of a way. So a subsequent version of SIMT targeted a new approach called the bring your own data structures approach. So the key idea of BIODs is to recognize that it's often desirable to step beyond the built-in representation that the engine provides for you. So an engine like Souffle or other things like that, there are different engines out there like RDFox and other things like that, but they all offer a pretty fixed set of relation representations. So in Souffle, you get to pick among things like B-trees, breeze, and other things like that. However, what if you want something like a union find-based representation, or some other representation like a transitive or something like that? Well, in this case, the engine's data structures can become leaky abstractions when the data structure that you need isn't really provided by the engine, because you might have to, for example, materialize more than you are willing to accept. So I have this example here, where we have this big graph, and if we take the transitive closure, of course, we get this massive explosion. And the issue is more than just these graph problems. It's impossible to write a Steensgaard-style points-to analysis in vanilla Datalog. So as of recently, Souffle offers eqrel, but it's kind of boutique, and it's only one solution. We offer a custom relation provider. So in a SIMT, you can write code that looks just like this, and it gives you the kind of performance you would expect. And I'm going to start accelerating the talk at this point, because I can see I'm going to run over time. I have so many slides. So I'm going to skip past some of the formalization and just say we offer kind of a two-stage protocol that operates at compile time and at runtime for implementing these relation providers. And again, I'll refer you to the paper for the rest of the details and show you some results. So a re-implementation of a Rust borrow checker. So this is something that was implemented by the Rust project. It was called Polonius. So we get 2x speed up in a SIMT, and this is on a single thread for that. We also get 1.5 to 2x compaction using our transitive relations provider. We can also see, if we use union find, that for some large graphs, we can improve time and space by quite a bit, and that's because we're compressing, throwing away some information. With Galois, we are able to write a fairly sophisticated analysis of LLVM bitcode. And so this little diagram down here is just trying to convince you that analyzing, doing control flow analysis is really just kind of a generalization of transitive closure, of course with a lot more special cases and rules, but it's morally quite the same thing. And I was very satisfied with the outcome here. First, we have quite good parallelization in a SIMT. So this is a one context-sensitive analysis of Apache HTTPD that enumerated 5.39 billion control flow points. So those are distinct points in the control flow graph. And at 8 threads, it took 26,000 seconds. And at 64 threads, it goes down to 9.7 thousand seconds. So we get good scalability there. So I'm going to kind of move on to the cluster part of the talk now. So for this work, we've built on fast parallel relational algebra. So our group has innovated in developing an MPI-based parallel relational algebra runtime. In our setting, tuples are distributed by hashing their join columns and assigning it to a bucket, mod n, where n is the number of processes. Right, so the relation is kind of strided across all of the buckets. Right, so we've got some tuples here and the various buckets to which they're assigned. But of course, if we're just hashing on the join columns, then because there might just be key skew in the join columns, that's not going to be enough to really get us a truly distributed implementation that has kind of good balancing characteristics. So there's a second layer of balancing, which takes all of the non-join columns and hashes those and gives us a sub-bucket, and then those are dynamically rebalanced over time. That gives us a mapping to a node. All right, so when I get my bucket, sub-bucket decomposition, I map each tuple in the entire problem, so across the entire system, to a machine. And then occasionally, we will need to rebalance. Right, so we'll need to split, I say or coalesce, but because it's all monotonic, that's not really something that happens in this case. So every tuple is assigned an ID, which is kind of its bucket, sub-bucket, relation. So we store everything as a 64-bit ID, which imposes some amount of maximum bound on the problem, but there's no problem in principle with making these larger. And then to implement joins, we have basically intra-bucket com that replicates the tuples across buckets, local joins that are sort of on a per-bucket basis, and then all-to-all communication that distributes the result of the joins to their proper buckets and sub-buckets. I think I'm going to skip past some of this and talk about our implementation in MPI. So we use some novel algorithms for all-to-all communication implemented by Kifan, which is a student of Siddharth Kumar's, who I collaborated on this work with. And she came up with this very nice idea of the two-phase padded Brook algorithm, which solved the problem of optimizing heterogeneous all-to-all communication in parallel RA. All right, so I think I'm just going to skip to some results here. There's a lot more to say. But I'll just show the main graph. And so this is a scaled context-sensitive analysis of a KCFA, which is a sort of core control flow analysis. We even have a newer version of the experiment that I didn't put in here that's actually a proper context-sensitive analysis of the Linux kernel that I'll show in some later results in a few slides from now about GPUs. And we get pretty acceptable scalability up to around 400, kind of 800 threads here. I think we never really saw this pay off because we weren't, in this case, really specifically engineering the analysis to be as parallel as possible. There's a lot of sequential work, and so there's not enough parallel work to be able to extract. So we've made some, we've kind of made some subsequent analyses that are much more obviously parallel and get even better performance, and they scale up to around 1,000 threads, which is still not really good enough to be truly high performance in the high performance computing space. And so that's something where we're kind of looking into now some different ideas, and I'll talk about that a little bit about the end. All right, so just to skip ahead a little bit, because I'm looking to leave some time for questions, and some of this is in a working draft that I can point you at. So the last thing that I'll talk about is harnessing the power of GPUs. So of course, GPUs are very powerful, and they're powering some of these novel innovations we're seeing in things like LLMs. But of course, the challenge with GPUs is that you have to write your code to properly adhere to sort of a SIMT structure. So any amount of branching in your code translates into sort of threads just kind of sitting around waiting, right? And so that's not 100% true on modern GPUs. It turns out there is some amount of task-level parallelism, but it's mostly true. And our goal with this work, so there have been folks who have looked at implementing Datalog on GPUs before, but none of them was ever able to beat a good CPU-based solver. And so we're really trying to come up with an engine that really effectively allows us to sort of hit the frontier of scalability and achieve kind of new results in that space. So one thing that you can kind of see here is that if we look at Soufflé's performance, and like I said, Soufflé is focused more now on memory compression than it is on speed. It used to be more parallelizable maybe 5-10 years ago, I think we sort of seen, if you look at old commits of Soufflé from a while back. But now they've kind of focused a little bit more on memory optimization. And the consequence of that is that we get pretty poor scalability after around 4 to 8 threads even.
All right, so this is a transitive closure of souffle on a large graph, a graph that we'll also evaluate on our GPU-based system in a while. And if we look, we can actually see where the bottleneck is. And it's that we see insertion happens sort of in a very serial fashion. And so as we increase the number of cores that we throw at souffle, we're still kind of bottlenecked by this serialized insertion into the tuple data structure. So I'll just kind of speak about this briefly because I don't have a ton of time left, but I'll give you the high-level idea of kind of what we've got going on here. So our solution is called Datalog. It's an implementation of a GPU-based Datalog engine that's currently implemented in C++, basically CUDA, as a bunch of CUDA kernels. So what you do is you take the fully planned IR from souffle, so we don't have a full compiler yet. There's still some amount of sort of manually taking the join plan from souffle, or having our grad students just figure out what it would be, and then implementing it to use our kernels. And then using our library, Datalog, which is well, we have variants of it. Our primary implementation is in CUDA. We also have a version in HIP, which is for AMD-based GPUs. AMD is really catching up to NVIDIA when it comes to memory throughput, but we haven't been able to get quite as good performance out of HIP yet because we really rely on having good memory allocators, especially high performance on CUDA. And so we haven't been able to quite get there with HIP yet. So we have our kind of application space up here: program analysis, graph analytics, deductive databases. We write these as Datalog programs, which we compile down to relational algebra kernels using all the techniques that I kind of talked about previously in the talk. And so this is kind of where we're starting at in the Datalog work. And then we have different relational algebra kernels like join, deduplication, insertion, merge, built on top of in-way joins or k-ary joins. And we have some novel techniques for handling those on the GPU as well. And then all of this is built on a novel data structure called the hash-indexed sorted array, which is a special tuple representation for the GPU that I'll talk briefly about. So the HISA, or the hash-indexed sorted array, is a multi-level data structure that establishes a mapping between a compact just data array. Of course, GPUs are great at working with arrays, and the underlying tuples stored in the GPU memory and a sorted index map. And this is really important for fast range querying. So the join column of each indexed relation is kept in sorted order. GPUs are fairly good at sorting things, right? So that's one thing. Although it is a little bit of a bottleneck, and that's something, in fact, we're trying to sort of get rid of in our current implementations. And then they're linked into the index map. And then the index map forms a hash table, sort of an open addressing-based hash table with linear probing, that stores key pointers in lexicographically sorted order. And each key of this sorted index map points into the underlying tuples in the GPU VRAM. So using this kind of multi-tiered approach that's at sort of under the hood, really built on sorted arrays, which GPUs are kind of blazing fast and really good at dealing with, we've been able to really innovate. And there are some more details available on our draft. So I guess just to kind of toot our own horn here, this was something that we were excited to see was kind of quite highly ranked on Hacker News a while back. And we got some excitement with people kind of using it. We have an implementation that's publicly available on GitHub. I'll just speak briefly. We have C++-based implementation of our API. And just to kind of cut through to the results, I'm showing here a transitive closure on several large graphs comparing souffle and a number of other GPU-based joins and Datalog systems. So GPU join is a competitor system to us. cuDF is an open source data frame library that people have used before for relational algebra. And we can see that Datalog, for example, on our largest graph here, takes 14 seconds versus souffle's 232 seconds. And then the two other competitor GPU systems just blow up out of VRAM because they don't sort of efficiently sort of compress memory. They kind of have to blow things up because they don't have this nice HISA data structure. And then, of course, the kind of big result here that I'm kind of excited about. So there's context-sensitive analysis of the Linux kernel, for example, and HTTPD and PostgreSQL. So we implemented these on top of GDlog, and this was from data from a paper from VLDB called GraphSpan, and that data set has been used by many other folks studying Datalog. And in Soufflé, it takes around 49 seconds, and in GDlog, it's 1.3 seconds, 13 seconds versus 0.3 seconds, and then 57 seconds for PostgreSQL versus 1.2 seconds. So we're able to see quite large speedups in practice. Now, I will say, in this specific application, and this is more of a criticism of the original paper, they're using method cloning, so they're pre-enumerating a bunch of parallel work that really can be leveraged by the system. So it's hard to say that these results would necessarily translate to what I would think of as a really nice, rich, context-sensitive analysis, but at least it's a good litmus test of the kinds of parallelism we can achieve. And just our most late-breaking work, we've got a new variant of this this engine that uses a column-oriented representation. And we've been able to see even greater results from that. So our new system, FVlog, uses this vertical, we call it kind of vertical data log approach, where we use a column-oriented approach, kind of like DuckDB or the similar kind of inspiration from databases. And on, let's see, on our largest graph, GDlog does 23 seconds. The other system, Soufflé, is 292 seconds. RDFox is 507 seconds. But we take 10 seconds. So we're able to get a speed up of 2.5x using this technique, and up to 200x versus the CPU-based systems like Soufflé. So I'll just say we've open sourced a lot of this work. So SIMT is open source. It's a crate you can just go use right now. Slog is something we've got currently on our GitHub repo. And then GDlog is also work that's in submission, but we've got an open source version of it on our repository as well. So thanks so much to these awesome folks that I've had the pleasure of working with, and especially thanks to the National Science Foundation who's funded this work. Let's see, I thought I had a slide here. Yes. So I didn't have much time to talk about logic programming beyond Datalog, but this is really just the beginning. So we really look forward to extensions of this work where you can really do true search. And so we're currently looking into variants like Datalog O, Datalog plus minus, answer set programming, and other things of that nature using this approach. So we're currently wrapping up the first year of our 5-year NSF project on this. And the next things we're trying to scale to GPU clusters. So that's something we've currently got working on right now. We're looking at doing heterogeneous communication for doing things like breaking apart big static analyses on a per component basis, workload partitioning, parallel I/O, and me personally, I'm very interested in building kind of the largest static analysis systems kind of in history. So thanks so much. I really appreciate it. And I'll take a question or two as we have time. Thank you all. Yeah.
So you're comparing against Epic machines.
Mm-hmm.
You're using the
I think for questions.
Right, I think it's for the stream.
Right. So, so you're comparing against server-grade CPUs.
Mm-hmm.
The H100s that you have, do they also contain the ARM cores? They would have, let's say, wider memory bandwidth than perhaps the AMD ones. Are you starting to look at those kind of machines as well?
So we are starting to look at some different kinds of GPUs, especially things that we can run on, so some supercomputers that we have access to, like Polaris, have some kind of unique GPUs that do have more memory throughput and things like that. One example that kind of impedes us there is that you can't exactly run CUDA on some of those systems. So we've tried to translate our work and our backends to things like SYCL, which is another kind of programming paradigm, and HIP, of course, is another one. So we've started to look into that a little bit, but I don't have a definitive answer for you as to like the exact details of the system right now. And if you'd like to chat offline, I'm happy to give you sort of exact details of all the stuff that we've tried. But that's a great question. We're very interested in using, for example, these AMD chips have extremely high memory throughput. I kind of alluded to this in the talk, but one big thing for GPUs that really allows us to accelerate is having high performance allocators. And so we don't have very high performance allocators on the AMD side yet. We think that's mostly a matter of engineering, and so I'm hoping that in the coming months we can achieve that as well.
Hi, Mitch from currently at Meta. So I'm wondering what kinds of CUDA kernels and what the compute memory bandwidth looks like when running some of these programs. Like, are these Datalog programs, when they're running on GPUs, are they mostly bandwidth constrained? Is there, I'm assuming a lot of these computations are not mapping to things like matrix multiplication. Sort of what does that look like?
Yeah, that's a great question. So they're all handwritten kernels under the hood. You're exactly right. You would be tempted to use matrix multiplies, but we've gotten more mileage out of just kind of handwriting our own kernels using HISA, for example. Not to say that there couldn't be another approach. For example, if you've seen the GPU-based points-to analysis from Matt Might, maybe 10 years ago or so, I believe he uses matrix multiplication in that work. So, there's other possibilities out there too. I would say I definitely think memory bandwidth is the big thing. We have experimented using some CPUs that have very high memory bandwidth, so specifically the Knights Landing CPUs that have HBM kind of built into them in the same way that a GPU would, and we've seen similarly higher performance. And so I really do think it's the case that, at least with this way of doing Datalog, it's really much more memory bandwidth constrained. And if you've looked at previous Datalog systems, they used to do things like keep things on disk because they had huge amounts of materialization. I think a lot of the leverage that we've been able to get has been the fact that modern data center GPUs have high amounts of VRAM. And so, you can get the H100 has like 80 gigabytes of VRAM. I would say we're limited in the sense that outside of a single GPU, if it doesn't fit in VRAM, if the fixed point doesn't fit in VRAM, then you're just kind of, all bets are off right now. So that's really motivating us to look into GPU clusters. So yeah, thanks so much for the question. And I sense that I'm essentially out of time. Is that right?
One quick question. And thank you, Chris, for your fascinating talk.
Thanks so much for your time, everyone.